is the Atlas humanoid robot. It lives in the WPI humanoid robotics lab known as Whirl. It is currently used by graduate and undergraduate students as a platform for robotics research.
Our project was specifically to develop a method for SLAM on Atlas. SLAM stands for Simultaneous Localization and Mapping, and it's a process by which a robot can build a map of its environment whilst developing an understanding of where it's located with respect to its surroundings. As far as we understand, this is the first implementation of SLAM on a humanoid robot altogether.
We use the open source middleware ROS and transportable controller TUF to communicate and control the robot. We also run and display our project fully in simulation, which provided helpful visualization for our 3D maps as they were generated. A variety of ROS nodes were created in both C++ and Python. This generates both 3D and 2D graphs, where Atlas can explore the unknown frontiers.
We compared maps made from the point clouds of both the stereo camera and the LiDAR on Atlas's head, and we found that the LiDAR point cloud was much better quality, but significantly slower than the stereo camera and more memory intensive. The stereo camera map had so many artifacts and shadows that it made path planning with the current algorithm very difficult. If the algorithm took into account the height of obstacles in the map, Atlas would be able to walk over uneven surfaces or over small obstacles, which would improve the usability of the stereo camera map. Until then, the LiDAR is the better option.
The robot eventually stops mapping when the entire 2D occupancy grid is complete. We call this closed-loop mapping. We were often able to evaluate our maps visually to see how accurately they resembled the robot's simulated environment, and we looked at the smoothness in structural features and artifacts, and also like random points on the map. And currently, we'd say we're getting very confident maps out of our algorithm. But we're being limited by the robot's path planning, and eventually, we'd like to test our solution in a robot in a closed space in Washburn Labs.
Allowing Atlas to interact with novel environments is a good step forward. Because of its humanoid design, it has potential to perform the same dangerous tasks that people might otherwise have to put themselves in jeopardy to do, like crisis response in a location wrecked by an earthquake. In unexplored environments like this, it's really important to be able to use methods that are broadly applicable to varying circumstances like SLAM.
Throughout the project, we had a lot of opportunities to learn new things. We explored topics that were new to us, like 3D SLAM and using C++ and Python together in ROS. We also had the opportunity to reach out to and work with other students and researchers to complete our project. In this project, we analyzed the data from the robot's sensors and created the first SLAM algorithm for the Atlas robot.